Um, Good afternoon, friends, and welcome to lecture 3. Today, I'll be not using slides, but it's more like a blackboard like scenario. Um, of course, I'll be using both slides and blackboard like scenario whenever I feel the requirement of it. The topic of today's lecture would be a review of special theory of relativity. So far, to just um, see what we have done so far is that we have studied uh, we have reviewed all the discoveries of quarks and leptons and also the gauge bosons, and we have given some sort of an overview of the subject. Now, from this you can understand that this subject requires particles which are extremely moving fast. So today we will be trying to do a review of special theory of relativity. I'll just remind you that this is just a review. I won't go into the details of the entire special theory of relativity in great detail. Okay, it will only be a review because I won't do a full course. I'll only amplify the things which are required for this particular course. What we need for the course, we'll just try to recover them and review them. Now, the first question to start off with, say, is why special theory of relativity? Why do we need special theory of relativity? Now, one can think of several reasons why we need special theory of relativity. One of the things, basic things, is that the particles which we are trying to probe are subatomic scales. So, for example, there are scales which are about sub-Fermi. So, if you have the size of these particles, so is around, say, this size is around 10 power minus 15 meters. So, it's around Fermi scale. So, if you want to probe this one through some photon or some other matter wavelength, the wavelength of this particular light probe, okay, or lambda probe, should also be of the same size or even greater, so that or even smaller, so that it can see the substructure of it, and the frequency should be relatively higher. So because these is all within the realm of special theory of relativities. So you need a very high frequency probes to probe very small particles. So very high frequency means very high energies. Typically you are in the realm of, okay, high frequency implies high energies. So this would mean you are in the realm of special theory of relativity. Okay, there could be other reasons also. So what could be the other reasons? And the other reasons would be the kind of experiments which we are looking at. Say, for example, we were looking at all the experiments which we are looking at involve particle antiparticle annihilation. Okay, so particle antiparticle annihilation means that there could be an incoming particle, there could be an incoming antiparticle which annihilates and then starts producing, say, for example, so a photon, and this photon should be able to produce all the other particles. Say, for example, it should be able to produce particles of, say, all the quarks, all the leptons, and so on. So what it produces, the energy of this photon depends upon the energy of the incoming particles. So what is the energy of the electron and what is the energy of the positron? This annihilation itself is inherently a relativistic process. Is inherently a relativistic process. So this means that suppose if you are producing quarks, leptons, so whatever it is, the mass of these particles will determine what is the energy required for the incoming electron and positron. Say for example, if you want to produce just electron positron, the photon should have an energy E gamma should be roughly 2 MeV. Okay, now that is fine because it's of the same energy level of the electron and positron. So mass of the electron and positron. Suppose if you want to produce muons, so E gamma should be 2 mu at least. Okay, now muon is roughly 200 times heavier than electron. So the electrons should carry masses at least 100 times. Each of these electron and positron should carry energies which are at least 100 times that of their masses. That means that means, as we'll see, that it means that their highly velocity is very high, so they are extremely relativistic. So it is important that inherently all the process which we are considering are essentially relativistic processes. And the third sort of experiments which we look, so these are all experiments. This is some sort of, if you want fixed target experiments, target phenomena, in which you probe, say for example, you take a proton and hit it with high energetic electrons. So this is some sort of fixed target. We'll come to it when we are doing in QCD. This is some sort of a colliders, accelerators. So all this phenomena again relativistic, because when the energy of the particle is coming mostly not from its mass but mostly from its momentum, so that is essentially relativistic part essentially. Okay, and the third example we have seen is cosmic rays. These are extremely energetic rays. Okay, these are extremely energetic rays, and which are mostly 99% made up of protons. And we have seen it's almost like a fixed target. Say for example, you have a detector here. So it could be some photographic plate or something. It could be a gas chamber or anything. Okay, bubble chamber. And then you have rays coming all over the place which are very high energetic, hit the air molecules inside this. So let me draw the air molecules in some other color. So there are all these air molecules inside this detector, hit and leave tracks on a photographic plate. Say for example, if there is some photographic plate somewhere here, these are the kind of tracks we have seen earlier. So they leave tracks on this particular. These processes are also highly energetic. These are naturally available. These are not man-made, and to deal with them also we have to do relativistic. So what we will try to see is to study review STR in the next 2 lectures, this one and the next one, and then try to justify all the statements. We need to have the tools to study this kind of phenomena. So this is precisely what we are trying to do in this the next two lectures. We will try to revise these tools, which will require, which will be required to understand this phenomenon. Now, just to understand what relativity is, let's just remember what is Galilean relativity. So Galilean relativity has the concept of frames. Say, for example, you have one x, y, z, say for example, and you have a vector here of some length, say for example. Okay, this is the origin, you can think of about it. And suppose if it moves in the x direction in with uniform velocity parallelly, okay, with uniform velocity with parallelly, there is another frame of reference which I call it as, this is theta prime, again x prime, y prime, z prime, and now you have another vector here. Now you can transform from x coordinates to x prime, y prime coordinates. Let me write x to be r, to be x, y, and z. So this length, so this is the axis, and this is some sort of distance from the origins. These are big axes, okay, sorry. And the another one, in this frame you have r prime to be x prime, y prime, z prime. R prime could be, say for example, I wrote it in terms of, say for r prime is this length of this vector, r prime. In principle, if you write it from the this is essentially the distance between these 2 points. Okay, this is 1 point, this is another point. Okay, this is the distance between these 2 points. So okay, r prime is this one. Now the consequences of Galilean relativity are one, as long as they are polar, the length of the vector remains constant. Say for example, mod r is equal to mod r prime. Length of the vector remains constant under Galilean transformations. I am not repeating the Galilean transformations. I am assuming all of you know these things. Okay, but I am not repeating the Galilean transformations. But you can put in the Galilean transformations and you'll see a couple of consequences. One, the length of the vector remains constant. Second is, now you don't have to do only parallel transport, you can also do rotations about a point. Even then, the length of a vector remains a constant. So what we have is that if you even rotate or even if you transform, okay, these are speeds, these are non-relativistic speeds. These are speeds much smaller than c. This is important actually. Okay, these are speeds which are much smaller than c. So for speeds which are much smaller than c, we have something called the Galilean relativity, which gives you the entire picture, and it tells you that under these transformations from one frame to another, you will have the length of the vector remains constant. There are two consequences, and under rotations also the length of the vector remains constant. Now we will go into the limit where this limit is broken. So we want to go to the velocities which are very close to c, which are pretty close to c. So we want to go into this limit where these velocities okay, are close to C. V is very, very close to C. Where C is as you know very well, this is the speed of light in vacuum. So this was done by Einstein, and there are the two postulates of special theory of relativity. One of the first things is the existence of inertial frames. What does it say? There are these frames which you can define it with distant stars and everything, which you can see, in which all the physical laws are same. Okay, all physical laws are same in these inertial frames. So all physical laws inertial frames. This is a very important concept. So the physical laws will not change, say, some Newton's laws or gravity or some. And all experiments should yield the same results. So it means if you do it with one frame and you do the same experiment another frame, the results should be the same. But moving from one frame to another is governed no longer by Galilean transformations, by some other transformations called Lorentz transformation. So if you have a frame theta 1, and if you transform to another frame theta 2, if you want to relate the same event in another frame theta 2, you had to at speeds which are very close to the speed of light, you can no longer use Galilean transformations, but you have to use something called the Lorentz transformations. And so what these Lorentz transformations are, we'll see essentially what these Lorentz transformations are. And then as a consequence of this, in fact, we can have infinite number inertial frames which are possible. Okay, so then there is this is essentially telling you that if you want to move from one frame to another inertial frame, so you have to use something called the Lorentz transformations, and all the physical laws are same in every frame of reference. So every physical inertial frame. There is another a very important second postulate, which sets the constant in every frame of reference. So in every frame of reference, there is one particular constant which remains constant under all frames of reference, which is the speed of light in vacuum. The speed of light in vacuum is the same in every inertial frame. So that means we have a constant in the theory, and this constant sets some sort of limit. Every time you have a constant in some theories, like for example, quantum mechanics has a constant which is called the Planck's constant. So that sets you the limit of when, say, quantum mechanics becomes important compared to classical mechanics. So speed of light is also the constant in the theory, which sets when relativistic effects will become important. So if you are reaching very very close to the speed of light, relativistic effects will become very very important. And this is speed of light is invariant under Lorentz transformations. That means it doesn't change under Lorentz transform. That is the reason why it is the one which we define the Lorentz transformations also. Okay. Now, now let me go further and discuss what is something called how do you define a line element. So to do all this business, let me introduce you some notation. The consequence of this, I'll tell you what are Lorentz, before coming to it. I'll introduce some notation. Now, Lorentz transformations involve translations in time also. So you can no longer treat. So, for example, here we have treated x, y, z, the space part, as something as only didn't care about time. Actually, we didn't care about in the Galilean transformations. The time doesn't transform, whereas in Lorentz transformations, the time also transforms. So you have to really define. Uh, uh, Time also as a coordinate, and that's the reason we'll try to introduce some notation. So in this notation we'll use something called the Einstein notation, so which is defined as follows. So we define x x mu is equal to ct x, y, and z. So we define, instead of x, y, z as a vector, we define t, x, y, z as another one vector actually. So this is one vector. Now I'll set c is equal to 1. So x mu will just become t, x, y, and z. So this notation is called Einstein. So this is, so if you want to get only the space part of this one, so x0 will be t, and x bar is equal to xi, that is equal to only the space part of it, x, y, and z. Okay, x0 is essentially the time part of it, and xi is equal to the space part of it. Now there is another, the same vector can be written in another form, but it's called some sort of in dual space. So x mu would be, there are two options here depending upon the sign of the metric, x, y, and z. This could be this depending upon sign of the metric, or this could be t minus x, y minus z. I'll tell you what this sign of this metric is essentially. So if you want to go, so one is called covariant, another is called contravariant vectors. To move from one covariant to contravariant to one covariant vector, you need to have something called the metric. This has definitions. One, there are two options here, or which are both used in literature. So if you use this, this will be the definition, and if you use this metric, this will be the definition to transform, say for example this one. So eta mu nu advantage is eta mu nu. So x mu is equal to eta mu nu x mu. So this is the definition. What does this do? If I write it in terms of column vectors, then you will understand it. So this is x mu, so t, x, y and z is equivalent to this matrix into again this column vector t, x, y and z. Since this is diagonal, so suppose if you take, so either you take the space part to be positive or the space part to be negative. So here the space part is positive, here the space part is negative. So you have to remember what is the sign of the space part. That's one way of remembering this. So I remember it, what is the sign of the space part, or otherwise you can remember what is the sign of the this one, the time part. So let me try to remember that the space part should always be positive. So then my metric would be would be minus 1 0 0 0 0 1 0 0 0 0 1 0 0 0 1. So that gives me minus plus. Okay, these all will be remaining plus. So that only gives me minus for this part. So the Einstein notation here is that I am multiplying this entire column vector with this matrix. Since it's diagonal, it only the t part picks up sign, and x, y, z will remain this thing. So any repeated indices should be summed over. So this is the repeated index here, which is given in terms of the Greek indices nu. So if any repeated indices, one up and one down, means it is summed over. Okay. So this is important that this notation will be used a lot in our course. So I want all of you to really focus on this notation several times. Many people miss this one, but just focus on this notation. There are several examples. I'll just note down. I'll give some assignments on this one. So I want to introduce. So this is called x mu is called a 4 vector. Anything with an index, and mu is called an index. This is called 4 vector index, also called Lorentz vector index. Once we have this definition, okay, we will try to define what is called the line element. So the line element is defined as ds square is equal to dx mu dx mu. So it's an infinitesimal point here around x mu and another infinitesimal distance, infinitesimal length of a vector. So similar to the Galilean transformations where we considered a small vector, say for example r and r prime. Now we want to ask the question, what is the small length of a vector? Okay, but this is a 4 vector. When I say a vector in Lorentz transformations or in Lorentz in special theory of relativity, it means it's a 4 vector. It contains also the time along with it. So I want to define something called an infinitesimal length of a vector. Okay, so this infinitesimal length of a vector is given this in this particular fashion. So let me expand this. Would be in our case. So this is nothing but uppercase. This is again. So let me expand this one. So dx mu is nothing but this column vector. Okay, 1 second. Okay, so this would be something like so this will be, if I expand this algebraically, okay, t square x, okay, minus t square x square. Okay, if I expand this, it will give me something like minus t square plus x square, or let me put it this way, this is minus dt square plus dx square, and this minus sign is coming from the metric. Okay, why is this line element so important? Actually, why is this line element so important? This is the line element. So we define the line element to be invariant. So what we say is that transformations, so if we have one frame of reference similar to what we have considered in Galilean transformations, so if we have a ds square here, in another frame if we have another ds square, these are very small, I just expanded it, so ds square prime. So under Lorentz transformations, the definition of the Lorentz transformations is that they should live under Lorentz transformations ds prime square, they should be equivalent to each other. So the ds square doesn't change under Lorentz transformation. Any transformation which leaves the Lorentz transformations invariant is, so ds square is invariant under all Lorentz transformations, or is invariant under any frame of reference. So this line element will remain same, and this is a property of all scalars. So this ds square is a scalar quantity, it doesn't have any index. This actually is a property of all scalars. What do I mean by scalars? Scalars are those objects which don't carry any Lorentz index. So all scalars will remain invariant under Lorentz transformations. So with this, we have come to one of the properties, main properties, and this is how we can also derive Lorentz transformations. We can start off by asking, what are the transformations which leave this ds square invariant under all under what are the transformations, and you will end up having Lorentz transformations. So this the equivalent of the length of vector, but in 4-dimensional space. Okay, so here I'll stop the part 1, then I'll continue with part 2 in the next